So we should have gotten all of our calculations done by this point, okay? As far as that problem is concerned, you do need to do the problem and do it at the end. You know, you've done your calculations. I need you to do your percent error, which using 10% as the actual value. So that would be a fourth calculation to do once you get the average. And you only have to do that one time using your average value. Okay, so you don't have to do percent error 3 times, only do it one time using your percent, your average percent. Okay, compared it to your 10. Now, if you had one that's way off of the other two, and the other two are closer to 10, you can just make an excuse, say we went way past. You know, instead of doing a 180, I did a 270, or you know, just something, you went way too dark, you know, we didn't pay attention. But you have to have a valid reason to be able to throw out a trial. Okay? So, tomorrow would probably be a good day. I think let's go ahead and plan to bring Princeton Review tomorrow. We can work the problems in there. We can look at some of the multiple choice questions. Tomorrow we'll go through, I'll go through some of the multiple choice off of old tests, so you can kind of look and see some of those type of questions that get asked. We've already looked at some from 2013 just in class, but tomorrow's review. Many of y'all, well not in this class, but well you guys are going to be going to the breakfast, so I will post a video of anything we talk about, and then Wednesday's the test. Okay, so that gives us then really 2.5 weeks, which will probably be electrochemistry before spring break, which means coming back, acids and bases, we're gonna have to really kind of go quickly. All right, this is year 2014. Okay, when heated, calcium carbonate decomposes according to the equation above. In a study of the decomposition of calcium carbonate, a student added 50-gram sample of powdered calcium carbonate to a 1-liter rigid container. The student sealed the container, pumped out all the gases, then heated the container in an oven at 1100. As the container was heated, the total pressure of CO2 in the container was measured over time. Have we gone over this one? We did do this one?
Yeah.
Do you have it in your packet? Is this one in the packet? No? Is it yours?
Is it in the first packet we got?
It might be in the first one. Just look for the graph.
Yeah, it is.
Okay. So the point here is this, is when is equilibrium established? When it flattens out, when the concentration remains constant. It doesn't go to zero, it doesn't go to completion, it just remains constant. Okay? So that's what I want you to be able to see from this. We did another problem where they just gave you data in a table. It reached equilibrium, again, when the pressure or the concentrations remain constant. So we need to make sure that we understand that point right there. So in this one, so notice again, the first thing it says, calculate the number of moles of CO2 in the container after 20 minutes of heating. Okay? Moles of CO2, well, we know the pressure, right? We know the temperature. I think they say the volume is a 2-liter container somewhere. No, it's a 1-liter rigid container. Okay? So how are we going to get moles?
Ideal gas.
Ideal gas law. Again, just notice how that shows up everywhere. Okay? They're not going to have a gas law problem. They're just going to include that into these other ones. Okay? What's the only thing that's going to be in the equilibrium expression?
The pressure of CO2.
That's all right. So the Kp is strictly going to be the pressure of the CO2. Why not the other one?
Solid.
Because they're solid. So remember, only aqueous and gases go into equilibrium expression. Kp is going to be all gases. All right? So Is there enough, so what's KP gonna equal in this? Which is what? At equilibrium, what's the pressure of the CO2? Well, it's it says at 1.04 down here. Okay? It gives you in the problem 1.04. The final pressure in the container was 1.04 atmospheres. So we know then that that's going to be the KP. So the last question says, is there enough information to calculate KP? And the answer is yes, because it's just going to equal that. All right? So, what we need to know for the test is you need to know how to calculate K given concentrations at equilibrium. And remember, there are 3 different ways in which you are going to be given concentration. You can be given it directly, all of them, which don't count on that. You can, that's just plugging into the equilibrium expression. You can be given an initial concentration and one of the final equilibrium concentrations. And then using stoichiometry and ice table, you figure out what all the equilibrium concentrations will be. Or the third way was you give an initial concentration and it tells you the percent that reacts. Okay? And I think it was 2019 or 2018, they gave one that was 47% reacted again. And so you just had to use that to figure it out. Okay, so that's the 3 ways they're going to give you concentration. Or we go the other way, you're given you're given K, what are you going to? You're going to be given KP and you have to find the concentrations. That's when we're going to use the ice tables in X, minus X, plus X, and all that. That with Le Chatelier's principle, but I think from that lab you had to quote Le Chatelier's principle enough times to where that should be something pretty straightforward as far as Le Chatelier's principle, what's going to happen, which way the reaction is going to shift. Okay? What do we do to K if you reverse the equation?
Inverse.
Inverse, because reactants become products, products become reactants, so it's 1 over. If I multiply the equation by 2, what do I do to K? You raise K to whatever you multiply by, because the coefficients are your exponents. Then if I add equations together, what do I do with the K's? Multiply. You multiply the K's. So if we had 3 equations like Hess's law, we have 3 K's, and we're going to add them. Now, one thing I do want to talk about that I haven't done is the relationship between delta G and K. All right? Now, this is really just plugging into a formula. If there's ever a question about delta G and or K, and if you recall on some of the thermo questions, they said calculate the value of K as one of the sections. We always just skipped over that one. Okay? But now we know how to calculate this, so we can calculate delta G as negative RT, natural log. Everybody understands about natural log, right? E raised to the power. So if I want to calculate K, now, hey, this is kilojoules per mole, this is joules. And you're going to use the 8.31 joules per something. I think it's joules per mole K. That value is always going to be given. But what are we going to have to do to these 2 things? Convert them, okay? And in this case, I would probably convert the G to joules instead of the R to kilojoules. Okay? So this is just plugging in. If we need to calculate the value of K, if you know delta or G from K, you just got to make sure the units on these 2 match. It's kind of like the same thing when we did delta G equals delta H minus T delta S. Delta H was in kilojoules, delta S is in joules. R is always calculated. This is given on your equation, on that equation sheet. This value is given. So whenever you have thermodynamics, you're going to use the 8.31. It's the same ideal gas law constant. You're just going to use 8.31. Okay? So, seems like there was a question in one of these problems that we did that had that on there.
2006.
2006?
It is 2011.
2001?
2011.
Oh, yeah, that one right here. All right, so 2011 is down here. Indicate the value of G. So you've went through, when we calculated 2011, write the equilibrium expression for Kp. Well, Kp is just going to equal what? I know, but what's just the expression going to be? The pressure of the CO2 again, right? Because it's the only, so it's very similar to the one, that other one. Okay? So determine the pressure in atmospheres of CO2 in the container. Well, again, the pressure is just going to be, okay, we can just go use this and use the pressure and use ideal gas law. Okay? Then it says the value of Kp for the reaction is 0.0012. So if I plug that into here, Anna, help me on. If I plug this into here, okay, what's the natural log of 0.0012? Is that going to be a positive or negative number? Okay, remember if it's a decimal, the exponent's always going to be negative. The natural log is always going to be negative. Log or natural log is going to be negative. If it's greater than 1, it's going to be positive. So I know that this term right here is negative, and since I have a negative and a negative, what's delta G going to be? Positive, because if K is 0.0012, is this reactant or product favored? That's reactant favored. Okay, so it wants to go this way, not that way as much. So delta G is going to be positive, meaning it's really pretty much a non-spontaneous reaction. It does go some, but it really wants to come back the other way. That's a pretty small value. The ratio of products to reactants is pretty small. Okay, so it's just going to be plugging in. Now, if they wanted you to calculate delta G from this, you would just plug in the 0.0012 into here. Then your R and the temperature is given as 423 K. You just plug those values in. You just go from there. Yes, ma'am.
For part 2, where do you get the moles and the volume?
Actually, I think what you have to do is use your Kp on that one. Since Kp is given, Kp is just going to equal this. So with the pressure of the CO2 is really just going to be 0.0012.
Oh. So you don't need to use.
No, you don't have to use ideal gas law. Okay, that would be my first instinct is to use it, but then she just went through and said, well, there is no moles or liters or anything, so you got to go to plan B. Okay, well, how else can I find it? All right, well, Kp is equal to this, so therefore, if I know Kp, I know that. Okay. All right, okay. Have a good day.